me record this. So the electric potential or electric potential difference, what letter represents potential? V. Capital V, so that we don't confuse it with velocity. And there's a lot of different ways we can write this. Electric potential can be KE over Q. What is KE there? From physics 161, what's KE? Kinetic energy, what's Q? Charge. So electric potential is the amount of energy you're getting out divided by the charge. Energy per unit charge. This could also be equal to potential energy if you just have potential energy in your system over charge. Or it could be equal to kinetic energy plus potential energy over charge. The big point, electric potential is always an energy divided by a charge. So what are the units of electric potential? What are the SI units of energy? It's from 161 too. Joules. Okay, that's good. That means I don't have to call up Dr. Iyer and yell at her. Because you remember joules. And I don't want to call up a pregnant lady and yell at her. That would be horrible. What about charge? Coulombs. So joules per coulomb are the units of your electric potential. It also has another name. What's the other name for the units of electric potential? Joules per coulomb. What is that? What's written on a battery? Voltage, volts. So that number written on your battery, that 1.5 volts, that is the number of joules per coulomb that battery puts out. So it's energy, energy over charge. And in electricity, we don't always use joules for energy. In electricity, we use a different unit. We use something called 1 electron volt. 1 electron volt is 1.6 times 10 to the negative 19 joules. So that's a more common unit of electrical energy. Okay, so there's electric potential. That's what it physically is. It's energy over charge. And there's different ways that we can set up an electric potential. We can set it up by making one of these. So let me do a positive plate and a negative plate. Bunch of positive charges over here, negative charges here. What's going to happen if I have some positive charges here and some negative charges here? What's going to be formed in the middle? Remember this from last chapter? An electrical field. Now where does the electric field go? Goes in the middle. So we can draw some electric field lines. And what direction? To the negative. Goes away from positive and towards negative. So I can set up an electric field. An electric field is going to create some electric potential. And that electric potential that it creates depends on D, the distance between them. Electric potential in between two plates inside of a uniform electric field is E times D. Electric potential is electric field times distance. That's another way you can get an electric field by setting up some plates and have electric charges moving between those. Any questions on that? And again, this is all a review of stuff that was covered in the lecture. And then the last thing we have an electric charge. We'll make this a positive charge. Where does the electric field go? Towards the positive charge or away from the positive charge? Away. Electric field always goes away from positive charges. So it's consistent with what we have in the picture up here. All these lines, the electric field lines, are going away from the positive and towards the negative. So electric field pointing away, and what we can do is we can take a little charge right here, little V, little point charge. We'll say that charge has a charge Q, and because that's now sitting in an electric field, it has an electric potential. The electric potential of this point charge is K times Q divided by R. where r is the distance you are from the thing that's making your electric field that you're sitting inside of. So if I have a charge that's a distance away from another charge, the electric potential of that charge is k times q divided by r. Okay? And what are the units of that going to be? And what are the units of this v going to be? Units of v. Volts. How about this one? What are the units of this one? Volts. V is V. Big V, they're all volts. Calculate them all different ways, but they all give you the same exact thing. They all give you physically volts, which is an energy divided by a charge. Okay. That's electric potential. And then the other second big concept of this is in the movie Back to the Future. If you've seen Back to the Future. What's the second big concept? Begins with a C. Capacitors. And what is the purpose of a capacitor? This was just on the quiz. Stores charge. It holds charge. If you open up your TV, it's got capacitors inside of it that store charge. A lot of times when a TV breaks, it's the capacitors inside of it that have swelled. They've stored too much charge. And what you can do is you can drive around if you're really bored, and you can pick up TVs that are on the side of the road. You can open them up, and you can just replace the capacitors, and they'll work perfectly. Then you can sell them if you're really bored. Okay, so capacitor, purpose of a capacitor is to hold charge. It's also to teach us about the home shopping network. Anybody know the name of the home shopping network? Not HSN. What's the other big home shopping network? QVC. This is how I remember this. Q equals V times C. That's how I remember that equation. Where my mom shops for Christmas gifts. Q. What is Q? Charge? You think it's charge? That's a big Q. Is that the same as little q? What's Q? Bad guy from Star Trek? Yeah, there's a character on Star Trek named Q. That's not what we're talking about here. What's Q? I got 1 vote for charge. Anybody have another guess? If you have another guess, we'll put you in a room, put you in a little pit, and let you fight it out. Let's just charge. It is. You're right. Q. Charge. Okay. How about V? What's V? You know, they've done studies that show that students have the attention span of goldfish. Do you know how long a goldfish's attention span is? The longest attention span is about 4 minutes. So, when did we last talk about V? Was it within the last 4 minutes? It was. So your attention spans are shorter than goldfish's? Or we're just really quiet. What is V? Volts. Voltage. Which is also known as potential, which is an energy over charge. And then what's C? Capacitance. And this is where things get confusing, because this is a capital C. What else is a capital C? Coulombs. So the units here are the same letter as this. So that could get confusing. Don't let that confuse you too much. But we have Q equals V times C. Charge is equal to potential times capacitance. What are the units of capacitance? So we know the units of charge. What were the units of charge again? So we're going to write this equation in terms of units. Units of charge. Coulombs equals units of voltage. What are the units of voltage? Joules per coulomb or volts. And what are the units of capacitance? It's the grade that you're all trying to avoid. F. And what does F stand for? F does stand for force, but we've run out of letters, so we're going to make F stand for something else. In terms of units, F, the units of capacitance are something called farads. I used to have exquisite handwriting, but something happens when you get a doctorate. As soon as you're called doctor, your handwriting just plummets, and nobody can read it, except for nurses. Any of you experience that? If you're volunteer at hospitals, you're in PT, so maybe you know. Doctors, shit handwriting. Nurses, they can translate it. I think they must take a course on reading crappy handwriting. So coulombs equals volts times farads. Okay, so there's capacitance. That's one equation we need to know for capacitance. We also need to know how we can combine capacitances in circuits and draw diagrams of circuits and how to add capacitors up so that when we go drive around, pick up the broken TV, we know what size capacitor we need to replace, what size we need to put in. So when we're drawing circuits, we tend to draw circuit elements in different ways using different symbols. We'll learn more of these, but for capacitors, capacitors are two parallel plates next to each other. So that's what stores charge. That is the symbol for a capacitor. And I can hook up capacitors in two different ways. I can hook them up in series. So if I imagine that I'm going through this little circuit, let me draw a whole loop. If I go through this circuit and I hit a capacitor and I have no choice but to go through that capacitor to get to the next capacitor, and I just keep going around and around, these capacitors are connected in what we call series. So let me call this first capacitor, we'll call it C1, call the second capacitor C2. And maybe I'm an electrical engineer and I've been told, oh, we're sick of assembling the circuit, we're sick of putting this together and using two capacitors. We want you to figure out what's one capacitor that could replace both of those. So we need to figure out, oh, what's the total capacitance there? What's the charge that I'm trying to store? And how do I add C1 and C2 to find out what kind of new capacitor I need? To do that, there's an equation. 1 divided by the total capacitance is equal to 1 divided by C1 plus 1 divided by C2. So capacitors in series, I think of them as adding weird. It's a weird way to add things. Okay, so when you add these two up, you take the fraction. 1 divided by C total is equal to 1 divided by C1 plus 1 divided by C2. So after you do this in your calculator, this thing, excuse me, I'm dying apparently. You need to flip it upside down. You need to take the reciprocal. So I also remember that when finding C total of something in series, I need to flip it. That's different than capacitors that are connected in parallel. In parallel, it looks something like this. And in this circuit is different than series. So if I go through this circuit and I get to this little point right here, I have a choice of where charge could flow, right? Once I reach here, where can my current go? I can go up or down. So if I have a choice of where I can go, then these two things are in parallel. Apparently I am dying. So I can go up or I can go down. If I have a choice inside of my circuit, if I can go a different direction, then those two pieces of the circuit are in parallel with each other. So we call this parallel. Parallel is normal. So C total of these two capacitors is just C1 plus C2. You straight up add them together. And it's important to kind of learn this now and get really good at this, because we're going to learn about resistors in a couple chapters, and resistors are actually flipped from this. Same approach, same math, same algebra, just slightly different way to add things. So let's figure out, let's look at some examples. First question, how many capacitors are in that picture? 3 capacitors. How are they connected? Series or parallel? They're all parallel to each other. 3 capacitors, 3 Cs, and they're all in parallel. Great. Let's draw another one. Let's draw, okay, Okay, how many capacitors are there? 3? Are these in series or in parallel? These are all in series, because they come right after, one right after another. Let's do one more. Let's do this. Go up, down. How about this circuit? How many capacitors first? 5 capacitors. Are they in series or parallel? Yes. Both. They're both. Oh, shit. What do we do when we have both? So I can go through, this is series, and then I keep going, I come to here, and these are in parallel, and then I keep going, and then this is in series. So what I can do is I can simplify this circuit, and we'll do a problem where we do this, where we go through and we try to simplify it so that everything's in parallel or everything's in series. So we do this in steps. So I'm going to go through here, series, up, parallel, and then series. So I have 3 in series with each other. That parallel one is really mucking things up. So I can combine these two so that it becomes 1. So then if I did that, if I found some equivalent circuit, some equivalent series, some equivalent capacitance, we'll call that C1, C2, let's make that C3, C4, and C5. I can simplify the circuit by doing C1, just leave that, C2, just leave that. I can combine C3 and C4, let's call it C34, the combination of both of those, and then I can do C5. In theory, how would I get what C34 is? What would be the equation for that? C34 equals what? C3 plus C4? They add normally. Why do they add normally? Because they're parallel. And then how about down here? How are these connected? These are all in series with each other, right? So I can get 1 over C total is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3, 4, plus 1 over C5. So I can do that addition. I can add it all up, and then I'll get an answer. My answer will be 1 over C total. What do I need to do to that? I need to flip it upside down in your calculator. If you don't know how to do that, I can come around and show you. There's various ways depending on your calculator. And then this whole thing, now I've saved my company bunches and bunches of money by figuring out, oh, we don't need 5 capacitors. We can just use 1 that has this capacitance. Okay? So we're gonna do a problem where we actually solve this out. Let's do problem number 60. Problem number 60 tells us, find the total capacitance of the combination of capacitors shown in this figure, and they give you a figure. Figure looks like this. Okay. C1 equals 0.3 microfarads. C2 equals 10 microfarads. I'm going to go ahead and suggest that everybody take out a calculator too so that you can calculate these things and make sure that I'm getting the right answers. Always test the numbers that I give, test the answers that I get. If you find that I make a mistake, if I calculate a number wrong, any day that I do that, I will give everybody in the class 5 extra credit points. So get those calculators out so that we can calculate things. All right, so what I want to do is I want to find what's the equivalent capacitance of this whole circuit. Again, this is problem number 60 in chapter 19 in the textbook, so you can read it there as well. Go through, I have my circuit. I have C1 is 0.3 microfarads, C2 is 10 microfarads, and C3 is 2.5 microfarads. All right, which capacitors are mucking things up, making my life difficult? Are they all connected in the same way?
Yeah.
Are they all in series? Or are they split up? So as I'm coming through, I can go to the left and go through this branch, or I can go to the right and I can go through this branch. So this capacitor is in parallel with these two capacitors. But then these two capacitors, they're in series with each other, right? So I have to simplify this side to get them both in parallel, and then I can simplify to one. So I'm going to first combine these two that are in series so that I just have two capacitors in parallel with each other. You get some intuition for doing that and how that works by practicing. There's no replacement for practicing. Just got to go through some problems. So let's do that, and we need to figure out what is C12. Okay. C1 and C2, to combine them together, how do I add them? Are they in series or parallel? Series. So what equation would I write down to combine those together? Do I add them normal or weird? I add them weird. So I have 1 over C12 equals 1 over C1 plus 1 over C2. So 1 over C12 equals 1 over 0.3. What does micro stand for? Remember micro? It's 10 to the negative 6. So 0.3 times 10 to the negative 6 farads. Plus 1 divided by 10 times 10 to the negative 6 farads. Plug that into your calculator. Let's see what you got. You all have nice fancy calculators. They don't pay me enough, so I had to buy the cheap one. Let's see if I can get the same thing that you can get. I plugged everything in, and I got this. I got 3.4 times 10 to the 6. Anybody else get that? Yes, ma'am. You did? Good. Multiple people getting that? So I'm guessing that's the right answer then. So we make sure that we can get that. And then what do I do? What next? I have to flip it, right? These measurements, this capacitor is microfarads. It's 10 to the minus 6. So if you add stuff up and you get something that's like 10 to the 6, that's completely different. That's like a million, not a millionth. That's the difference between 1 and then 6 zeros, and then 6 zeros and a 1. So if you get a really, really big number, take a look and make sure that you didn't forget to flip it. Right? We need to flip this to get what C12 is. We take the reciprocal, and we will find that C12 is equal to, cheap calculator says, 2.9 times 10 to the negative 7. Farads. Okay, so make sure you can get that. Plug that into your calculator. If you're not getting that, call me over, let me know. Okay, so that's what C12 is. And then I want to combine these two to give me just one capacitor. We'll call it C1, 2, and 3. How do I get C1, 2, 3? There's it.
C12 plus C3.
C12 plus C3. They put an air conditioner right above my head. I can't hear anything. Okay, so C123 is equal to 2.9 times 10 to the negative 7 farads plus C3. What was C3 is 2.5 times 10 to the negative 6 farads. So I get C123 is equal to something. What is it equal to? What do we got? 2.79 times 10 to the negative 6 farads. So that's the equivalent capacitance. Anybody ever used the defibrillator before? Do you know what defibrillators are? Some of you have used them before? You've used the practice one? Okay, so once you know how they work, they build up a whole bunch of charge. The thing inside of the defibrillator, it's capacitor. It's holding lots of charge. You got the two paddles, that's two parallel plates. And you build up a whole bunch of charge, and then what do you do when you stick it on somebody? You do a little clear. Why?
Clear.
To make sure nobody else is touching them, because what happens to the voltage? Voltage goes into the person, tries to restart their heart, and if you're touching them, then you're getting that voltage too. And you get a jolt to your heart, which you probably don't want. So what we want to do now is we want to kind of level things up a little bit. We're going to kick it up a notch and do something that your book doesn't really talk about. We're going to find Q, V, and C for every single piece of this circuit. So we're going to give you a little guide for how to do this. The equations that we need to know for finding Q, V, and C inside of a circuit. If we are in series, we find the total capacitance by adding up the reciprocal of each individual capacitor and flipping it. Doesn't matter how many I have, I can do this approach for adding all the capacitors I have in series. Just need to remember to split it. And then a key here is that in series, charge that goes through one capacitor is the charge that goes through all the capacitors. Charge is the same in series. And voltage in series will get split up. And then in parallel, How do we add capacitors in parallel? Just add them up. Nothing special. What do you think is going to happen to charge in parallel? If charge in series is the same, what do you think happens to charge in parallel? It's going to split. Everything can't be the same. It's got to be difficult. But then voltage, what happens to voltage? Voltage in parallel is the same. Really, really useful. And then the last equation we want to know is Q equals VC. This little bit of information right here that's in that box, I would put that on my equation sheet. This is how you can solve any circuit problem involving a capacitor. So let's see how that works. Let's go back up to our problem. Here's our problem number 60. And let me say that I'm going to take some amount of voltage. I'm going to take, let's say, 500 volts. And I'm going to put 500 volts into this circuit. So there's 500 volts flowing through this whole thing. What happens to voltage in parallel? Stays the same. So I come down and I have voltage going through the left side and voltage going through the right side. It's going to be the same voltage through each of these sides, right? Yeah. And what I want to do is I go to the very, very end, the very, very last little circuit, and I'm going to work my way backwards to figure out what those voltages and currents are, and we'll show you a little trick to do that. So C123, I know the total capacitance, right? That's what the total capacitance is. So in that part of the problem, I also need to know what's the total voltage. 3 things I need to know. What are the 3 things I need to know? 3 things that we can solve for this. Capacitance and what else? What's the shopping network? Charge and voltage. Q, V, and C. So I want to know Q, V, and C for every single part of the circuit. Down here I found this is C total. This is the total capacitance. Do I know V total, the total voltage? Yeah? What is it? 500. How do I know that? I just made it up. I told you that's what it is. Okay, so V total is 500. Okay. What's the last thing we need to find? Q total. Can I find Q total? Yeah? How? How?
Because you were given the other numbers.
Say it louder.
Because you were given the other numbers.
Because I was given the other numbers. So what equation do I use? QVC. So I can take Q total, and I can take V total and C total, and I can multiply those two together to get the total charge that's inside of this circuit. So when I do that, let's multiply those together. What's the total charge in the circuit? So this is what, 2.79 times 10 to the minus 6 times 500. I got 1.38 times 10 to the negative 3 coulombs. So that's the total charge. That's all the charge that's inside of the circuit. So I know everything about this particular capacitor. I know its capacitance, I know its voltage, and I know its charge. Now what I'm going to do is I'm going to go backwards. I'm going to go from this circuit up to this circuit. What changes from here to here? I go from one capacitor to 2 capacitors, and how are these capacitors connected? These are in parallel to each other. So what I'm going to do is I'm going to go look at my little guide. Let's look at my little guide. And I'm going to look at parallel. And in parallel, charge is going to split. Voltage is going to stay the same. Okay? So what I know is whatever voltage I have right here, the voltage is going to stay the same up here as I go backwards, because this is in parallel. So how many volts are going through C12? 500 volts. So let's say V12 equals 500 volts. Can I find what charge 12 is? How do I find charge if I know voltage and capacitance? Multiply those two together and we can find what that capacitance is. That is 500 times 2.9 times 10 to the negative 7, and I get 1.45 times 10 to the negative 4 farads. And then I can also find, I know C3 we were given 2.5 times 10 to the negative 6. V3, how much voltage is going through this capacitor? Same, 500 volts. Voltage here, same as voltage here. 500 volts. And what's the charge? 2.5 times 10 to the negative 6 times 500 was 1.25 times 10 to the negative 3 farads. And then something crazy happens. If I take Q12 and I take Q3, that's all the charge that's floating around in this thing. So what should those two add up to? Those will add up to the total charge. Now I know everything about this part. Let's go back one more. I'm going to go from here back up to here. What changes between here and here? Here I've got two in parallel. What changes? I fiddled with this. This capacitance goes to being, how are these connected? Series. So what's going to stay the same between these two? Charge is going to be the same. So charge in 1, 2, which we have written here, is going to be the charge in 1 and the charge in 2. Okay, so Q1 is going to be 1.45 times 10 to the negative 4. And Q2 is 1.45 times 10 to the negative 4. I know what C1 is. C1 is 0.3 times 10 to the negative 6. Can I find V? Now I want to find the voltage. How do I find V? Yep. So I have my equation Q equals VC. If I divide both sides by C, then my voltage is charge over capacitance. So we have 1.45 times 10 to the negative 4 divided by 0.3 times 10 to the negative 6. And I got, try it again, 1.45, 10 to the negative 4. I got 483 volts for V1. And now there are two ways that I can find V2. I can use the same approach, Q over charge, Q over capacitance, the charge divided by capacitance C2. What's the other way I can find it? What do V1 plus V2 have to be equal to? 500. They have to add up to the total voltage. Each line of this has to get 500 volts. So 500 minus 483 gives how many volts? 17. So we should get 17 volts there. And now we found charge, capacitance, and voltage in every single part of the circuit, and simplified the circuit, worked down, and then worked our way back up. All a puzzle. Not too bad, and you just do the same approach over and over and over again when solving these. Any questions on this? This is what you can anticipate kind of being one of your exam questions, probably solving something like this. Write this circuit, and then write the charge, voltage, and capacitance in every single one of the circuit. Okay, so practice those. There's a couple in the homework to practice. That's all I got for you for today. You still got about 20 minutes to work on, 25 minutes to work on homeworks. Okay.